I'm going to talk to you to discuss about reverse time migration using the Poynting vector. This is a kind of imaging technique in our geophysics department and in all over the world to image the subsurface. What is the reverse time migration and what it can do, and etc. We will discuss about it. Actually, reverse time migration is kinds of wave equation migration. So we can use the wave equation in forward modeling and the backward modeling in reverse in time. And then we try to do the cross correlation between those of them. Actually, what we are going to do in this reverse time migration, usually we have the workflow is computing and storing the snapshot of the forward wave field. The forward means going down from the surface. And the second one is computing and storing the snapshot of reverse time backward wave field, meaning the reverse time down to the up. And then after that, we do the cross correlating of the forward and backward wave field. Okay, to make it more video, I want to talk to you. I want to show you this video. So see, can you see the forward modeling? Yeah. So this is the forward, and this is the backward. Backward. Then we do the cross correlation. In this reverse time, so see, the forward is going from the surface down to the subsurface. Reverse in time is in the opposite direction. Then after that, we do the cross correlation. What do we mean by cross correlation? Cross correlating means we are doing the correlation between two different functions. If we say this is autocorrelation means we are doing correlation between the source wave field and the source wave field itself, or the receiver or reverse back in time reverse modeling wave field with itself. This is auto. Why do we say cross? Because we are doing correlation between two different functions, which is the forward and the backward. This is what we mean by cross correlation. So if we have two functions f and g, autocorrelation means f with f, and cross correlation means or autocorrelation means f with f or g with g, and cross correlation means f with g. Okay. What RTM can do here? We have some examples of three different kinds. The first one here is from BP, which is the subsalt imaging. It can detect the steep dips in the complex subsalt region. This reverse time migration also can image the hydrocarbon exploration can image the fault imaging as the traps of the hydrocarbon. Also, it can try to image the basin as arranged for a geothermal model here, as these people do, as the research do. This is geothermal exploration at the 11-mile canyon of Nevada. This is the above figure is the synthetic test, and the below figure is the real data test. Of course, it also has the limitation, or it can generate artifacts as a drawbacks. In these talks, what I'm going to discuss to you is the way to remove these artifacts. What do we mean by artifacts like this? See, this is artifacts, and this is artifacts. I can explain more why do we say this is artifacts, because we are going to start from the velocity model. We have here a velocity model, linearly increasing. See, can you see the arrow? Yeah, the arrow here is going linearly increasing, and then we have changing velocity model, not linearly, but like a constant changing here, and about 2 to 3 kilometers at the depth of about 1 point something kilometer, and then it's continues to be linearly increasing. So the velocity model here that we use for forward modeling is using this linear equation, and there is a reflector here. See, what I mean by reflector is like this linear velocity model in the step of 0.5 kilometer at about 1.5 kilometer depth. So the synthetic shot profile for the source at 3 kilometer, we can see here, this is the source shot of the source at 3 kilometer. We can see direct wave and refracted waves and multiples here. Here multiples. And this is the resulting in the figure 2. We have the resulting RTM images. As we remember before, RTM is cross correlation between forward and backward wave field. For the figure A, we have, this is before muting. So we have seen here some figures which has artifacts, which has noise. Then the artifacts, yes, we can say as noise. And we are going to remove this research is has focus on removing the artifacts. And after muting, we can see in the figure B, after muting with velocity of 1.5 kilometer, we have the image is without the artifacts. We can see the removal of the artifacts, and then we have still the artifact in the black arrow down here, around here. I think, yeah, this side. This is from multiple. So I'm going to discuss about you what kind of wave is this, and by like giving you an example here. Example here I have in the left side. Can you see in the left side? Here we have constant velocity model, and then after that it is linearly increasing using like linear equation. Not like this. It's not similar with the right side, but it's like I want to give you an illustration what happened if we have a linearly increasing model. Okay. So what can we have? Write this. Can you see? What happened after this wave undergoes a linearly increasing velocity model? It's like diving. Now, before it's this wave is going to the linearly increasing model, it is like directly propagating. We can say this is direct wave. We have direct wave and we have diving once the wave undergoes linearly increasing velocity model. Do you agree what I say? Diving, if you are swimming, gone, and you are jumping from upstairs, and then you jump to the swimming pool, you will feel like you are diving, something like this. Yeah, this is diving wave. Yeah, this is exactly what happened in this. But here, what happened from 0 to about 1.5, it is linearly increasing, and then we have step velocity as a reflector, and then linearly increasing again. So in my observation here, we can see a diving wave here, and then it starts to have refraction here because we have like a reflector, because once we have a changing velocity from low to higher velocity, usually we have refraction. Then we have a diving again. So this diving and refraction, it's considered to be the noise that we don't need to get, because what we want in the RTM image is just the image of the subsurface without the noise of the waves generated. Okay, let's continue our discussion right now. This is also the generated artifacts from an example of a marine shot. Okay, in figure A, this is before muting, and figure B, it is after muting. We can see that after muting with the velocity of 1.2 kilometer, we can remove these artifacts. This is also refracted waves because of different changing velocity in the cell layer. Okay, what happened here actually, this is RTM image also showing artifacts due to the wave field backscattered from the strong velocity contrast. We have here salt, you can see salt here, the salt boundary. So the wave is backscattered because of this high velocity difference between this boundary. In figure B, we have subsurface imaging points. Also, this is imaging condition with impedance matching, which means that we fix the impedance, acoustic impedance multiplication between density and velocity as a constant here. So we can see what's the difference. And then in figure C, this is window correlation, which means we show only within a time window following the first arrival. So this impedance matching in figure B is not successful to remove the backscatter wave in the short domain, but Windows correlation can remove the backscattering source wave. See, we don't see the backscatter wave. Do you get why there is no backscatter wave here? Because we just do it in a certain window time. Okay, there is a way here, because our point of discussion is how to remove this. We are trying to discuss about how to study the reverse time migration using the Poynting factor. So what is the Poynting factor actually? This is a measure of flow of energy, which is a mathematical tools for determining the direction of the wave propagation. The definition of Poynting factor is the multiplication between velocity and the pressure here, pressure wave field, which minus sign. And actually, this velocity is like proportional or equal to gradient of pressure times the first derivative of pressure wave field. This is velocity. So the imaging condition, at first, it has like this pressure source wave field multiplied by back propagated wave field over the weight of source wave field squared. And we know, do you know the cosine formula for this? I think and we have the factor. I think I should use yellow color here. Yeah, if we have factor A, this is factor B. So with the cosine, with the angle theta, so the dot product between factor A and factor B is like the magnitude of factor A times magnitude of factor B cosine their angle. So it's like giving the same example of this, but now this Poynting factor is not A, it is V times Vs, which is actually a factor also. It's just different different giving name to this. A is what is A and what is B, but here A is VSV times PS and B is VG times PG. So, and by the end, and the last question 5, we can have this actually, yeah, just giving the weight times cosine angle theta. So now we are going to exclude the opening angles which has greater than 180 degree, and then we give the additional condition here. The weight times cosine theta is equal 1 for cosine theta, which is greater than minus 0.5 and 0 elsewhere. Okay, maybe it's not a little bit unfamiliar. Do I need to discuss about this? Maybe if you have any question for this, I can explain it later. Anyway, yeah, let's us continue first. Yeah, this is the source wave field. Okay, the source wave field And the receiver, S stands for source wave field, and R stands for receiver's wave field. And this V is the Poynting factor, and this K, I is in X direction, and this K is in the Z direction. And both of them are for the source wave field. This is the source wave field, and this is the Poynting factor of the source wave field going down, which is forward. And here is the backward wave field, which is going up or reverse in time. And this is for the receiver, and this is for the this is the I or X direction, and this is the K or Z direction. Okay. So what happened here actually in the figure 7, we are going to remove this figure A. It correspond to figure A here in the right side, and this figure B correspond to figure B in the right side, which is the same as the previous figure in figure 2 using the linearly increasing model and left reflector in the middle. So here before muting, and this is after muting. After we apply the imaging condition to exclude the angle greater than 120 degree, see, do you see what's the difference between these two images? Yeah, you see, this is the same. This is RTM image, and this is also RTM image. But in this left side figure, we don't see the noise here. The noise upper, this is upper noise, down side noise. We don't have it in the left figure. Am I right? See, in the right side, we have still noise. This noise, I can say it as the noise coming from low wave number. I can explain to you what is low wave number. So see, this is more having no noise here, but we still have noise. Okay, in this figure, see, in this figure, what do you see? This is actually a salt, and the figure the left side, this is a salt domain, and this is also the salt, but it has backscatter wave as the noise that I want to remove. So after applying our condition, imaging condition, the right side of the figure, it becomes the figure in the left side. So our imaging condition works very well once we apply the excluding the angle greater than 130 degree. So in conclusion, we have been successfully handling the turning waves and the multiple arrivals for using this RTM method, and we can build a reliable velocity model building to image the subsurface. Do you know what I mean by subsurface? It's like anything below surface that we want to explore. Like we are trying to find the geothermal, we are trying to find the hydrocarbon, we are trying to find water traps. This is like we are trying to find the image, the traps or the structure of the subsurface using this method. So here also we apply simple muting, like with the velocity of some certain velocity, or we also try to window the correlation in a certain window, or we can apply this technique, which is imaging the conditions, using the imaging conditions like excluding the angle of greater than 120 degree to consider the wave propagation direction as the Poynting factor means to remove the artifacts based on the diving and backscatter waves. That's it. I think it's a good time to have a Q&A question. I think you may have question. I will be more than happy to discuss with you. Mhm. 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 Yeah. Okay, I can understand what your point of question. I think your question is how do we relate this mathematical formula to the noise, right? Actually, I can say this is the source wave field, the wave number, and this is the wave number of receiver wave field, or we can say this is receiver, this is source, okay? And this is the angle, opening angle. So we remember in the physics or in mathematics, we have the vector here. This is the resultant. So if the angle is between 0 to 90 degree, we will have this resultant is high wave number resultant, right? But if the angle is greater than 90, we can say, or between, we can say greater than 120 degree, 120 degree. So the vector is, we can say 180 maximum, right? This is the K of receiver. This is K of source. This is 180 degree. What happens if I have this vector? It can be 0, right? Or it can be low. Low wave number, if I have low wave number, it gives me the noise or the artifact. If I have the high wave number, this is smooth. That's why I want to exclude the angle greater than 120 degree, because I want to remove the noise. Okay. Because I want to remove the artifacts. That's why once we have the angle greater than 120 degree, which means cosinus of 120 degree is minus 0.5. So we have this cosine of 120 degree is minus 0.5, right? Okay. And if you want to exclude greater than 120 degree, like for example 180 degree, what is cosine 180 degree? This is minus 1, which means cosinus minus 1 after multiplied by W, it must be 0. That's why for W cosine 1, it must be 1 for cosine theta greater than minus 1 or equal to minus 1, which is less than 120 degree. But if you want to make it, we want to exclude the angle greater than 180 degree, we have to exclude the W cosine theta, or we have to make it 0 for theta greater than 120 degree, for example, 180 degree. Because less than minus 0.5 is minus 1, for example, it is cosinus of 180 degree, must be 0. That's it. Okay. Thank you for your time, my friend. See you next time. Hello. Assalamualaikum.